All right, lesson 2.2. What I'm going to do first is I'm going to open up Powerschool Learning. Whoops, I actually unfavorited. I want to open it. So I want to open up Powerschool Learning, and I'm going to get into my class. The lesson 2.2, what that means is it's chapter 2, lesson 2. So go to the chapter 2 folder, and I ask you to do a couple things today. When you get to the chapter 2 folder, first, I'm going to kind of read off of the 4 things you have to do. The number 1 thing is show up. And in this particular class, we're missing 3 out of 29. So 26 of you have already accomplished that. You've shown up. The number 2 thing you need to do is sign the attendance sheet, which again, 26 out of 29 have done. The next is this in-class work. Go ahead and click that. I'll point out that down below you will have homework on this lesson. It'll be due Thursday of next week. But I'm going to click on number 3, in-class homework. This is where we submit all of our stuff from our packets. When that opens up, for you, it should just be a start exam. And you should get what I have now up on my screen. So start the exam and get there. Now, secondly, what I want to do is I'm going to open up today. We've done a lot of algebra. I'm going to show you some calculator tricks. I want you to open this up in a new tab. The way to do so is if you're on a Chromebook, use both fingers and tap with both fingers on the Desmos. If you're on like a Mac or something with a mouse, right click and hit open a new tab. If you're on a cell phone, when you click, hold that button, hold your click on the icon, and it'll ask you to open a new tab so that you have all these Desmos calculators I've programmed. Okay, so that's what I want you to have open right now. Number 1 says if f of x equals this, what does that symbol mean? Inverse. And I'm going to go to make it its own page. This is saying, what is the inverse? Now, y'all might know the algebra. What's the algebra required to solve for an inverse? We switch x and y. But now I'm going to show you a technique of using calculator. If you go to the Desmos pre-programmed chart, you'll see that graph number 5 is an inverse. And it has that symbol over in that column. I'm going to open up that graph. So please open up from the Desmos pre-program graph number 5. You're my 3rd class of the day. I'm going to tell you what I've been seeing. The students have done this wrong in previous classes, or they're just opening up a blank Desmos graph. What I'm about to do will not work if you just open up a blank one. You need to open up my number 5 Desmos pre-program. You should see these 2 parabolas. Now, all my pre-programmed graphs, I write down the directions in there. I give notes and all kinds of things because I'm expecting you to use this at home throughout the year when I'm not there to help you out. So I want to make sure you know how to use them. So if you ever open one up, you can just read the directions. It says first, graph the original function as f of x below. And then it tells you it'll show up as red. So f of x is right here. I'm going to type in my equation on this line. My equation is not x squared minus 3x minus 2. This is my equation. So I'm going to change the problem. Does anybody know how to get a fraction line in Desmos? You can press slash, which is your same button as the question mark by the shift key on the right side, or you can open up your Desmos keyboard and look on there for the division button right there. So division, the numerator is 2x minus 5. The denominator is 3x plus 4. So now how many people have a graph that appears like mine? Show of hands. Great. Quite a few. I'm going to continue reading instructions, giving the rest of you a few more moments. The direction says if there's no restriction, leave that restriction as is. We don't have a restriction here. It says nothing about restriction. So I'm going to move on. And it says the graph of the inverse will appear in blue. The reason you see 2 graphs is my graph is already calculating the inverse for us. So what are we going to do with this? I'm going to move this tab out for a moment. And back on the tab of where we were typing in our answers, our Powerschool Learning, I want you to notice, you see how there's multiple choice options for number 1? Yeah. I'm going to do something that you could call cheating. It's technically not cheating because you're not stealing answers from everybody. It's just you're kind of using technology to do the work for you. What I'm going to do is I'm going to graph these inverses. I'm just going to type in the equations and see which one overlaps my inverse graph in blue. So option 1 is that the equation, and I'm just going to type in the math portion, 4x 4x minus 5 over 3x plus 2. When I look at that, let me change color so we don't have so many in red. I'll just choose green. Does that green graph overlap the inverse, which is blue? No, so that means it's the wrong answer. The correct answer will be right on top of that blue graph the whole way. So the first answer on mine is incorrect. I know they're randomized, so yours might be different order. I'm going to try the second option now. 2x minus 3 divided by 5x plus 4. Is that answer perfectly located on top of the blue graph? No. What does that mean? It's the wrong answer. So I now try the next one. Negative 4x minus 5 over 3x minus 2. Does that perfectly overlap? What does that mean? That's the answer. So we just discovered this is the inverse. So I'm going to go ahead and write that down, the inverse here. The inverse we just got from the calculator, which again, I understand it's kind of cheating, but I wanted you to see how you can use technology. We said it was my third equation, negative 4x minus 5 divided by 3x minus 2. Now you'll notice that I, on the answer choice, included a domain restriction. And that's, if you remember with domain, this is a great time to review this with domain. What is the one thing you're not one thing, two things you're not allowed to do in domain? Can't divide by what? 0. Can't divide by 0. And also there's something with a square root. Square root of negative. Okay, this problem has division. And so what we were just saying is you can't divide by 0. So if I looked at the picture of the graph, you would notice, where's my window for that go? You would notice this, the inverse goes left forever, right forever. There's just one break in the middle. That break, when you start the domain process, you first assume, okay, if we're dividing, that break's going to be at 0. That's what we first assume. And then we start looking at the problem and doing transformations. We'll find out that that 0 is going to change, but the graph will go left forever. It'll go right forever. You can divide by negatives. You can divide by positives. We just can't divide by 0. And so I take the denominator, which is 3x minus 2, and I would solve that as does not equal 0. This is the math to get that portion of the answer. And so I would add 2. And then if a 3 is next to x, how do you isolate that x? Divide. And so I'm dividing by 3. And look what we get. X does not equal 2/3. Isn't that what the value said right there? Yeah, so that's how I got that. Now I wanted you to know I did calculator to get from here to here, but if you were to do algebra, you would switch your x and y. That's what would happen. So questions on how I cheated to get the answer on number 1? Okay, number 2. Number 2, and I'm going to get myself some more space here. Asked to find the domain and range for both the original and the inverse. I'm going to cheat again. We already got our domain of the inverse. We already found that. So here is my domain, or there is my inverse equation. We already got the domain of the inverse. The domain we said was x cannot equal 2/3. Okay, I'm going to cheat again. And the cheat this time is not based off calculator. It's based off of knowledge. So maybe it's not cheating if it's based off of knowledge. There is a relationship between any function and its inverse. And it happens to be the math that's required to get from here to here. What's the math between these two that makes their relationship for an inverse? What math do you have to do to get from a function to its inverse? You switch x and y. Using that, I'm going to cheat here. X is the same thing as domain. So if we have the domain of the inverse, we have a piece of information of the original. If we know the inverse's domain, what do we know about the original? We know its range. What's its range going to be? Does not equal 2/3. Range goes with what letter? X or Y? Y. So we'd say Y does not equal 2/3. You see how I cheated there? Now I'm going to use this one's domain. The originals we'll do a little algebra to solve for this one's domain, and that will give us the range over here. Okay. So what are you not allowed to divide by? 0. So I'll just do this off to the side. 3x plus 4 cannot equal 0. Let's solve this to get this one's domain. What would you do first? Subtract 4. So 3x cannot equal -4. And then do what next? Divide by 3. So now we found this one's domain. X cannot equal -4/3. What does that mean about the inverse's range? Y cannot equal -4/3. Okay, did that make sense how I just came up with that?
Yeah.
It was based off the knowledge that what's the relationship between a function and its inverse? Switch in X and Y. So I kind of cheated there. I only did 2 pieces of algebra and I got all those different answers. But I say it's cheating because we didn't do that much algebra. But truthfully, it's not cheating in the sense of get you kicked out of school, that type of cheating. All right, so that was number 2. Now, the thing we did not get to last lesson that I want to hit now today is solving complex algebra. We have been through chapter 1. I've been just grinding it out, doing algebra. Starting today, I'm not going to force you to grind out algebra. We have so many technology tools. I know a lot of you use Mathway. In previous math classes, pre-COVID, you use those calculators and you insolve. Is that true? Y'all know insolve? Okay, I have a calculator I made on Desmos that I want you to practice today on how to insolve, because I want you to get to know Desmos really well. Here's the reason why. When we get to second semester in particular, Mathway will not do all the stuff we need it to do. If it did, I would just use Mathway. It doesn't. So we need to use all the pre-programmed I've created in second semester. For that reason, I don't want to be explaining how to use Desmos all at once when math gets really, really hard. Second semester, it gets tough. You might have thought chapter 1 was tough. Just wait till second semester. Math gets tough. So what I'm going to do now is I'm going to make sure we understand Desmos before the second semester rolls around. So what I want you to do is go back to your Desmos pre-programmed list and click on the insolve. It's graph number 1. Let's put it at the very top so you can see it. Insolve here looks a little bit different than it did on the Inspire. You can't just type it in a parentheses and say math menu 3-1 like we used to. You're laughing because you've done it before, huh? Time or two?
I was like, what you just did.
Okay. Well, anyways, I pull up this equation. Here's, again, all my pre-programmed. I give you instructions on how to do it. It says here in the first equation, or first line, to insolve an equation, first type the entire equation in. I'm going to tell you the mistake a lot of students do is they don't type in the entire thing. They type in everything but one side of the equation. You type in the whole equation. So I told you earlier, where could you get this third root button? Where is that located?
The Desmos,
Desmos keyboard? Now where? Functions?
Yeah.
Now where?
Miss.
Miscellaneous, good. Now where? Yeah. So third root, x plus 3 minus 6 equals -5. Truthfully, that is showing you the answer wherever it goes through the x-axis, but nothing is clickable on that red line. Technically, that is the answer though, just so you know. So how do I make it where it's clickable that I can get the answer? You follow the next 2 steps, or the next step right here. It says, secondly, graph y equals the left side of the equation. Now, here's where a lot of students are like, what's the left? Let me ask you, what do you think is the left? What do you think determines the left and the right?
Or the equal sign.
The equal sign. That's what divides it. We're going to type in y equals the left side. This is the next line. We're going to type in y equals the left side. And then you're going to type in y equals the right side. This is step 2 right here. So underneath, you're going to type y equals the left. I'm just going to copy that since I already typed it in once. If you highlight it on your keyboard, if you hold down Control and press C, it'll copy it. And then you can come over here and then hold down Control and press V. So C like cat, V like Voorhees. Control will copy and then paste it. There's the left side, and then the right side just -5. So I'll type that -5. The intersections of the 3 graphs are the solution. So when you graph this, you should have 3 graphs intersecting one another. That's the solution. And specifically, this note tells you it's the x value, not the y value, but the x value where they cross. The answer to this problem is -2. X equals -2. Do you want me to work out this one by hand, or you just want to trust it's -2 and move on? Trust it? Okay, I want to make sure you know how to insolve. I just walked you through one. I have a problem here. It's not in your packet. You're going to have to get it off the screen. I want you to try to do this one on your own using insolve. My insolve, not Mathway. I want you to try Desmos. I'll give you a couple minutes. All right, so now I'm going to move on and start 2-2. So with 2-2, what we're moving into is we're going to look at polynomials. So tell me, what's the word polynomial mean?
More than one.
More than one. We're going to look at terms that are more than one. Quick, high level. I'm not going to walk through on this problem all the steps we did last class. What I'm going to show you is make sure you know how to use Desmos if you just have to graph something. You see how this just says graph?
Yeah.
Do I need to use insolve calculator? Okay, different question. Do I need to use inverse calculator? If you're just going to graph something, what can you click? Blank graph. So I've had a lot of students ask me that. If you're just graphing, which one do I click? If you're just graphing, just get a blank graph. And I'm going to graph this first one, and we'll make just a couple observations, and then I'm going to move on. And we're going to race to example 2. So here's the graph. Draw a quick sketch. It doesn't have to be beautiful, but just draw a quick sketch. Yours probably not going to be as beautiful as my sketch that I just drew. What? Beautiful. Look at that. Quick observations. This graph is not centered at the origin. This graph is centered 3 to the right. Why is it centered 3 to the right? -3. What can y'all tell me about inside? It lies. So this goes right 3. Okay, what we're going to get into, this is a teaser for the end of the class. The reason it lies. Has anybody ever wondered why does X lie to us? Because it's our X. It's always telling those lies. Here's the reason why. Mathematically, when you go to solve this with X's, you solve for them being equal to 0. You might be thinking, wow, that was a terrible little mumble there. Let me try that again. You might be thinking, so why does that matter that I set it equal to 0? Because when you set it equal to 0 and you go to solve, you have to do the opposite of everything you see. And that's why it lies. What is the opposite of -3? +3. And thus, we get the value X equals 3. That's the X-intercept. That's why it lies. If you're ever wondering, that's why it works that way. And we're going to get there today at the end of the lesson, Lord willing. Different question. Why does this graph go down? Why does it not increase? Why does it decrease? Because it has this vertical reflection out in the front. That makes it negative. So that's just a quick review right there. Vertical reflection, which if it's a vertical reflection, it crosses over the x-axis because it goes from the top to the bottom, which you have to cross the x. So there's your notes for example 1A. I think I also gave you, how many more here? 2 or 1 more or 2 more? Let's see. Just 1 more. Example 1B. Let's graph this one. Yes, ma'am. Go for it. Example 1B. This graph says 2 minus x to the power of 5/2. And so here's our picture here. And I need to double down on something I did not explain very well a few days back, but I kind of just was fine with it because I knew this day was coming. But I'm going to do a better job now of explaining some things here. So here's your graph. Draw a quick sketch as best as possible. That's quick to represent graph here for example 1b. I want to point something out. This has a positive 2 on the inside. Does inside lie or tell us the truth? Lie. So we would think a positive 2 would shift us to negative 2. This one doesn't. And you might be thinking why. And the other day I just told you, just know math rule that if you have a reflection of x, the inside doesn't lie. And you might have been thinking at the time, you might have forgotten, you might be thinking, why does it not lie if you have a reflection of x? Here's why now that I'm showing you the algebra. Because ultimately you would be solving this problem. 2 minus x equals 0. And the easiest way to solve this is not to make the 2 lie and shift it across. The easiest way is to move a negative x. What's the opposite of negative x? And look what we get. X equals what number? 2. Thus, it goes that way. So ultimately, if you ever get broken down on when does x lie, when does it not, just set it equal to 0 and solve it. Question. Bonus points for who remembers this from last class. Why does this graph, why is it like, it's basically, it's cut in half. You didn't know that. It's cut in half. It only has 1/2. Why does it not exist on both sides?
Because the denominator is positive. It's even, sorry.
Because the denominator is even. If the denominator is even, it only exists on one side. But this graph does not go right. It goes left because it was a reflection of x. Reflection of x makes it go to the left, but it's only half because the denominator is even. Very good, Mark. Peyton, were you going to say the same thing? Okay, okay. All right, so that's all I was going to hit from there, Sue. I'm going to let you do example 1. You can probably find out the answer without even graphing it, but if you want to use Desmos, go for it. I'll give you about a minute. Time for some fun stuff. New stuff. Leading term test. So I love the leading term because this simplifies the most complex problem. The most complex problem can be simplified using what's called a leading term test. Now you might be thinking, what is a leading term test? I'd love to answer that question for you. A leading term is the highest powered term in a polynomial function. So I'll say that again. A leading term is the highest powered term. So when I look at this long problem here, here's a polynomial. Remember how polynomial means more than one term? Yeah. I'm looking, this is a long polynomial term. There's a 1, 2, 3, 4, 5. Okay, there's 5 terms there. The leading term selects the highest powered term. What is the highest powered term in this problem? 3x to the power of 4. Well, here's what I'm going to do. I'm going to write down here leading term. What we're going to find out. Do you want me to tell you or you want me to show you? Okay, the leading term is 3x to the 4th. I will show you first and then I will tell you. So here's the graph. 3x to the power of 4 minus x cubed plus x squared plus x minus 1. So there's the original graph. And what I'm telling you the leading term is 3x to the power of 4. Okay, are these two graphs identical? Are they identical? No. All right. What if I'll even make this closer. What if I change the graph to this? And I ask the question now, would you might think that might be looking identical now? Maybe a little bit. Okay, what if I do now? And I ask, hey, are they identical? And you hadn't seen anything else. Now what you'd be saying? They're looking pretty close, aren't they? What a leading term does is it tells you if you zoom out what the graph's going to look like. Like there might be all this other mess in the equation. There's all this other, pardon my initials, BS going on. But ultimately, the graph just looks like 3x to the power of 4. Okay, that's just telling you a general idea of what the graph will look like. And so how does that help us? Well, if we were only needing to find the end behavior, that means the end behavior, if you've forgotten, that means the limits as the graph goes forever to the left and forever to the right. The end behavior is talking about the limits as you go forever left and forever right. You could solve this without a calculator by using the leading term test. You could say, all right, my leading term is 3x to the 4th. And I learned on lesson 2.1 that there are 3 rules to graph a power function. Remember, power function means one term. My leading term is now one term. We could say, all right, rule number 1 was direction. I could discover, is it positive or is this negative? What is the case of the leading term? Is my leading term positive or negative? Positive. It's positive 3. Since 3 is greater than 0, we know it's in the first quadrant from lesson 2.1. Rule 2 told us, if you remember, the shape. You could look at your power and you ask yourself the question, is my power, there are 4 shapes. Is my power shape 1 where the power is greater than 1? Is it the second shape where it's equal to 1? Is it the third, between 0 and 1, or is it negative? Which is the case here? Is it greater than 1, equal to 1, between 0 and 1, or is it negative? Greater than 1. If you remember, that means it's going to curve to the y-axis. So anytime you have a positive power, you start at the origin, and as it goes out, it just needs to start to curve more and more towards the y-axis, kind of like that. Finally, we had the third step, which was the reflection. We talk about the left side. Does this reflect evenly, oddly, or not reflect at all? If the power is 4, does that reflect like an even, like an odd, or not at all? Even. And the even means across the y-axis. So this would, on the other side of the y-axis, curve to the y-axis over here. So that's my picture. Now you could answer the limits even if you hadn't graphed. I know over here we had the graph the whole time. You might be thinking that yourself, like, Mr. Voorhees, you have the graph. Do we really need to do it? Yes, I just wanted to go review over that. Tell me, as you go left, what's my graph doing? There's 4 options. It's either rising, going up forever. Could be falling, going down forever. It's getting really, really flat, or it's stopping at a point. What happens as you move left forever? It's going up and it's rising. And so the answer to this limit would be it's rising to positive infinity. It's going up to positive infinity. Now what's happening on the, that was left side. What's happening now on the right side? As the graph moves to the right and continues moving further and further right, does my graph rise, fall, get flat, or come to a point? Rise. It rises to positive infinity. And so that would be my end behavior. We could do that without ever having graphed the problems. So now to make sure I'm not just talking too much, what was the point of this establishing the leading term? We could get a high level view of what the graph would look like. Now, is that going to be the exact graph? No, when I zoom in, you realize that the exact graph had a little extra little music going on down there, shifted down and whatever else. All right, let's look at example B. So I'm going to ask you the question. To find me the leading term. I'm going to give you a few seconds. I'll just yell it out yet. Which term is our leading term? 3, 2, 1. I hear negative 3x squared. That is incorrect.
It's
2x to the 5th. Because is the leading term the first term? No. It's the greatest exponent term. So the leading term is 2x to the 5th. I am fully aware we could graph this in Desmos. This time we're going to do it just by our knowledge off the dome. We got to pick up our street cred. So when you run into someone on the street, you can graph stuff on your own and impress them. Because I know that's impressive stuff these days. Number 1. Will this graph be positive or negative? Positive. A is 2, which is greater than 0. So which quadrant are we eliminating?
4.
Quadrant 4. Number 2. I have a power here. What's my power? 5. Is 5 greater than 1? Oh, y'all already just answered that right away. Okay, so which way is it curve if it's greater than 1? To the y-axis. The other options were equal to 1. Equal to 1 is a straight line. If it's between 0 and 1, it curves to the x this way. And if it's a negative, it's a C curve, just to give you those rules again. So curve to y, straight line, curve to x, or a C curve. All right, and then finally, rule 3. What's going to happen on the left side? Even or odd?
Goes through the origin.
Or through the origin and diagonal across. So it'll curve towards the y in this quadrant down here. All right, so let's do our limits, because that's what this problem was all about. It asks about the end behavior, which means specifically the limits that go left for forever. So what I'm doing is I'm kind of racing to write limit f of x equals, remember f of x means y. So you're trying to establish what is y doing as x approaches negative infinity, as x moves left. And then the other limit will be as x goes right. So x to positive infinity. Okay, I got a question for you as you look at it. What is the graph doing as you move further and further left? Is it rising, falling, getting flat, or coming to a point?
It's going down.
It's falling. So what's the symbol that represents falling down? Negative infinity. And what happens as we move right? Is this graph rising, falling, flat, or coming to a point? Rising. And so what's the symbol for rising up? Positive infinity. It's almost as if limits aren't quite so impossible to us anymore. I like it. All right, I got one more here. Part C. Part C, leading term. 5, 4, 3, 2, 1. Yep. Now, even if you didn't, you forgot how to do this later on, you could always just graph this problem to solve for the end behavior, but we will use this. Rule 1. Let me get my x and y axis. There we go. Rule 1. Positive or negative? Which is less than 0. So which quadrant am I eliminating? 1 or 4? 1 is out. We're going to be in graph number 4. Rule 2. My power is a 5. Which way does a fifth power curve? Or I'm sorry, is it greater than 1? Equal to 1? Between 0 and 1 or negative? Greater than 1. Thanks. So it's positive. So you start at the origin. You curve it down towards the y-axis. And then rule 3. What's going to happen on the left side? No reflection. Reflect evenly, reflect oddly. Odd. 5 is odd. So if odd goes across the origin, so this is going to reflect towards the y-axis this way. I'm going to give you a moment after I write out my limits here. Let you think of what you think the answer is going to be. What you should be processing is as I go left, is it rising, falling, getting flat, or coming to a point? Then as I go right, rising, falling, coming to a point, or getting flat. What happens as you go left? 3, 2, 1. It's rising. So what's the symbol for rising? Okay. And what would it mean? Different. I'm just going to get trick. I'm just going to totally switch to the problem. What would it mean if I put a 0 there? What would I be saying?
But y equals 0.
If x is going to infinity, that would technically mean it doesn't stop. It's going and going and going. But what does the 0 mean? It's flat. That's the answer. If you had this, it's flat. What if you had this? That means it stops at 4. At the x of 4, y of 0. Okay, but that's not the answer for this problem at all. This one does go right forever. As you go right forever, what happens to the y? It falls. And so that would be the answer. All right, it's time for you to try one. DOL number 2. I would suggest, if you have to use Desmos, go for it. I would suggest trying to use the leading term test without Desmos and to predict your answer here. Example 3. Example 3 now, we're going to now focus on the inside. So if the leading term examined what's going on, really, if you zoomed out, now we're going to start to focus in on zeros, what I would call like a zoomed in idea. What's happening really close inside zeros and what we call extrema, meaning maximums and minimums. As a reminder, zeros are where they cross the x-axis. So in this case, this graph has 1, 2, 3 real zeros that you can see. 3 real zeros. And I'm using the term real because I'm about to explain what a possible zero is. So that's 3 real zeros. That real means they're really there. You can really see them on the graph. Those are 3 real zeros. And this graph also has a certain number of extrema. If you remember, extrema means maximums or minimums. These 2 points here, we would call those minimums. And to be more specific, very good. Why absolute? Nothing goes lower than those 2 points. This right here is a maximum. Is it a local or absolute max? That's a local because the graph does go higher, or relative, you could also say, at other points. Okay, so now with that aside, that was review. What's new here? When you look at the leading term, and this problem, what is the leading term? Okay, the leading term can also tell you other information. If the leading term is 3x to the 6th, what that leading term can tell you is that this will have at most, without looking at a graph, that this will have at most 6 real zeros. So a lot of people will call them possible zeros. It will have 6 possible zeros. What does that mean? The number of zeros that are possible goes off the highest power. This power was a 6. Since it was 6 to the 6th power, there's 6 possible zeros. Did this graph happen to have all of them? No, but there were 6 possible. And it tells you the most number of turns, or extrema. Extrema is a maximum and minimum that occurs when a graph changes direction. It can change direction at most 5 times. And you might be thinking, wait, why 5 if the power is 6? Is that a typo, Mr. Voorhees? No, that's not a typo. The number of turns in a graph or changes of direction is always 1 less than its power. And I'll walk you through, I think you'll know this. I think it'll click when I just give you some basic examples. So here, I'm just going to go off the grid here for a moment, off the packet. Go wild here. So hang on. Let's just say your equation was y equals 3x. It would look something like this. Here's y equals 3x, give or take. What's the power over here? 1. That means it has at most 1 0. Does this graph have a 0? Yes, it does, right there. You would have at most, it's always 1 less. At most, 0 extrema. Oops. Extrema. So will a line ever change directions? No, it's a line. It just continues on. It never changes directions. So it would have 0 extrema. Okay, now let's go 1 up. Let's say the equation became let's say the equation became 3x squared minus 2. What shape is 3x squared? A parabola. So now I'm looking at a parabola that's been shifted down 2 units. So now, at most, how many zeros could this graph have? Why 2? Because that's the highest power. There's only 2 x's at work here. So the highest power is 2, so at most 2 zeros. And then how many turns am I telling it could it have? 1. When you check the graph, how many zeros does this have? 2 zeros. And then how many changes of direction does it go through? Or how many minimums are there? 1. So you see it's always 1 less. For the record, you won't always have all your zeros or all your turns. For example, if this graph was over here, how many zeros does it have? None. So even though zeros, not extrema, zeros, it has none now, even though this would be like the equation plus 2. Even though it has a power of 2, it doesn't always have to have all the real ones. So with that background, let's look at this problem. I want you to examine the equation and just determine what is the leading term here. 3, 2, 1. X cubed. I'm just going to abbreviate and say LT. Are you all okay with that? What does LT stand for? Leading term. Okay, so if my leading term is x cubed, how many possible zeros? That says state the number possible. How many possible zeros are there? Possibly 3 possible zeros. That's factoid number 1. How many extrema could there be? Extrema just means maximums or minimums. How many are possible? 2 possible extrema. They won't necessarily have them, but that's what's possible. Now it says, then determine all the real zeros by factoring. I'm not going to do that. I'd rather spend the time later. So what I'm just going to do is graph it, and we will establish where the real ones are. Plus 5x squared plus 4x. The real zeros occur at -4, -1, and 0. I'm going to write those out. The real zeros here. The real zeros. X equals -4, -1, and 0. I'm gonna mark that in. Okay, so question over vocabulary. What's the difference between a possible 0 and a real 0? The real 0 actually happens, and you've verified it's there on the graph. The possible, where do you get that from? The power of the leading term. It's the power of the leading term. That's the difference. Okay, so be very careful when you see those words, what they mean. Future note. In coming days, we will learn about imaginary zeros. The real plus the imaginary will always add up to equal possible. So let me write that out. This is a future note for the future here. Future. The real zeros plus the imaginary zeros, which we haven't got to that yet, but it's coming. Real plus imaginary will equal the possible zeros. So if you don't see it on the graph, it's going to be what we call an imaginary 0, and we'll get to the math of that later. Okay, just so you know, the district will sometimes call this total. Will equal the, they'll sometimes say total zeros instead of possible. All right, your turn. You don't have to graph this to get your answer. Because of that, I'm only going to give you about 15 seconds. I want you to examine the problem, find your leading term, and then make your, from there, your observations on which answer is correct. All right, so now This slide's just telling you that we can do X method when powers are greater than 1. I taught you this on the first day. So again, I'm not going to hit the math here. It's because the very first day of math, I taught you that to do X method, you don't have to have it squared. When we did our steps, I taught you just to split the power, and you could solve. And that's all this is trying to say here. And so it's walking you through how to do the math. I've already shown you how to do the math. I'm going to focus on some later math here. So I'm going to do this the same possible way, or the same way we've been doing earlier. What is my leading term in this problem? In this trinomial? X to the 4th. That's my leading term. So my leading term here, my LT, if you will, is X to the 4th. Tell me, what is going to be true that you know about how many possible zeros could it have? 4 possible zeros. Very good. 4 possible zeros. Now, how many possible extrema could there be? 3 possible extrema. As you look at this picture, how many real zeros do you see? 4 real zeros. We don't know where those are. I can get -1 and +1, but I have some decimals. Let's go figure out where those are. I'm going to use Desmos here. X to the 4th power minus 4x squared plus 3. And I'm just going to click these to get my real zeros. So going from left to right, the real zeros here. X equals -1.732. -1. Watch this, I'm going to blow your mind. You see how this is a +1? Whoa. Whoa, plus or minus 1. And that's a +1.732. Boom. Looky there. You're welcome. Life-changing information right there. What does plus or minus mean?
It can be both.
It can be both. It can be positive or the negative. Yep. Okay. So those would be the real zeros. If you want to see the math to factor that out, if you go to the old YouTube videos I made, I do all that math work for you. But for right now, I'm going to just keep it quicker. All right. Your turn. DOL number 4. This one, I think you're going to have to graph to get the correct answer. I don't want to speak too soon, but I think that's the case. Yeah, you need to graph this to get the right answer. I'll give you a few minutes for this one. All right, example 5. What we're going to now talk about is, the problem looks the exact same, but I'm going to add in a piece of, I'm going to give you an example of what multiplicity is, an example early. So here, the problem itself, if we just wanted to solve the problem, we would do everything we've done before. We would state the leading term, what is my leading term in this problem? 5x to the power 3?
No, sorry.
I mean, X.
X to the power 4. Okay, so Jordan, how many possible zeros? My leading term is x to the 4th. How many possible zeros do I have?
5.
If it's a 4, 4th power? 4. All right, 4 possible zeros. Good, thank you. We have 4 possible zeros. And Luis, how many possible extrema could I have? 3 is correct because it's always 1 less. 3 possible extrema. Okay, the real zeros, we could type into the calculator, but this one, they happen to be good numbers, so I can just use this graph. The real zeros occur at, it looks like x equals 0, -2, and -3. So here, let's write these out. X equals, these are the real zeros. Real zeros. X equals -3, -2, and 0. Okay, I'm going to ask a question to you. So I want you to understand this. How many real zeros did we write down? 3. How many possible zeros are there? 4. Now, I gave you a little equation earlier, and I said real plus imaginary equals possible, which would make us think how many imaginary? 1. We would think that. We'll learn in the next class that was wrong. This actually has all 4 real zeros. That 0 occurs twice. You call it multiplicity 2. 0 doesn't work as a positive or negative. That's a good thought. But this 0 itself occurs twice. And you might be thinking, well, Mr. Voorhees, how do you know that? Because I look at the graph, there is something different about this 0 than the other 2. What's different about this one compared to the other 2? It makes an extrema. It changes direction right there like a parabola. The only way it makes a parabola on the 0 is if that 0 occurs twice. The equation for this, I might blow your mind here, I might not. I can tell you the equation just by looking at this example here. The equation here in factored form, if you went through and factored all this like it says, what you would end up with is the equation x plus 3 in parentheses. Where did I get the plus 3 from, do you think? A good thought, but from the graph. It's from the graph. Okay, why did I put it as a plus 3?
Because the x lies.
Because inside lies. Okay, so this next one, would it be an x minus 2? An x plus 2. And then this is just an x by itself. 0 is just by, there's no, 0 doesn't do anything. You don't need 0. So it's just x by itself. But because it made a parabola there, it's actually x squared. And I'm going to prove this to you, that I'm not just making something up by graphing this equation. Plus 5x cubed plus 6x squared. Okay, here's the equation they gave me. And now I want to type in exactly what I just rewrote down, that it's going to be x plus 3 and x plus 2 and x squared. And I messed this up, didn't I? X plus 3. What can you tell me about those two graphs? You see how they're exactly the same? I got that using the knowledge of what we know about our zeros and what's called multiplicity. So multiplicity exists whenever a curve or whenever the 0 occurs and it has like a curve to it. So these two went through like a line. So that just means they occur just one time. It's like the first power. But this one made a parabola, so I knew it was squared there. That's how that works. Now I'm about to give you that on a whole nother equation that's easier to see. So let me first let you do yours. Use your knowledge, use a graph to come up with the correct answer to DOL number 5, and then I'm going to show you what I just did in detail again. Example 6. Let me now walk you through this, what they call repeated zeros or multiplicity. So this first problem, it says to apply the leading term test to find the end behavior. When you look at this in factored form, that's what we call this. This is factored form, not standard form. Standard form is when it's a bunch of terms that are adding and subtracting. When you have here factors, that's factored form. To find your leading term, you have to multiply anything that has an x together. So out of the factors, you multiply anything that has an x. So the leading term will be x times 3x, 3x times x squared. I just drop all the terms that don't have an x, and I'm going to multiply this through. What is x times 3x? 3x squared. So that's 3x squared, and that needs to multiply with x squared. I don't need that parenthesis anymore. What is 3x squared times x squared? There's 2 x's, there's 2 more x's. How many total x's is that? It's 3x to the 4th. So this overall, if you were going to look at part A here, would generate a problem where you have a positive graph, because A is 3. A is 3, that's positive. So which quadrant is it not going to be in? The 4th quadrant. The power is greater than 1. So which way will it curve? To the y. And the power is even. So what does that mean for the left? Across the y-axis, you're going to get, if we zoomed out, we're going to have a graph that looks like that. Now that's what we established on this part. So this says to do the end behavior. So to do end behavior, that's when the limit goes left forever and right forever. So you're going to look at what's happening as we move to the left forever and right forever. Does it rise, fall, flat? What's happening? Come on, Jordan. What's happening as we go to the left? It's rising. So what does the symbol represent rising? Positive infinity. And what happens as you move right forever? It also rises up to positive infinity. Okay, so that's part A. Part B asks you to determine the zeros. So this is really simple in factored form. You can get the zeros straight from the equation. This x is by itself. That is x equals 0. That is a 0 right there. That's a real 0. By the way, we could establish from the leading term that there are at 4 possible zeros. 4 possible zeros. And there's 3 possible extrema. I didn't write that down, but I will add that now. From the leading term, we also could get that. On this, we could get the zeros. The way you do that is you take each factor and you set it equal to 0. And this is why inside lies. As you solve this, you'll realize why we say inside lies. Because when I solve this, I set it equal to 0 and I have to do the opposite of what I see. What's the opposite of plus 1? Minus 1. And so I have 3x equals -1. But I actually need to isolate this x. What's the opposite of multiplying by 3? Dividing. And so we have a 0 of -1/3. And finally, I have this last 0 right here. I would take x minus 2 and set it equal to 0. What's my one step? Add 2. And we get x equals 2. So it appears, if you line them up, it appears that you only have 3 real zeros. That's how it appears. I did this in numerical order, but that's not true. I actually have 4 real zeros. Even though it only looks like 3, one of them counts twice.
0.
Not the 0, but the one that has the power 2. This one counts twice. So we would say multiplicity of 2. And so all 4 zeros are real on this problem. There's no imaginary. They're all 4 real. All right, part C just tells us to find a few additional points. I'm going to skip that. And part D would then ask to graph. I have your graph right here. There's the zeros that we just found, but I'm going to leave it as is. What I'm going to do here is let you try your DOL. Specifically, all I need you to find is the multiplicity and the zeros. I want you to establish what the zeros are and the multiplicity. All right, now we're going to finish up looking at this ACP problem. It says Mike is given this equation. I apologize, mine is blurry here. Let me try to zoom it. I didn't clear it up too much, but it has this equation and it says where A, B, C, D, and E are all. All right, let's take a look at example 7. So example 7 says the table to the right shows a town's population over an 8-year period. Year 1 refers to 2001, this is 2002, and so on. Create a scatter plot of data and determine the type of polynomial function that could be used to represent the data. And so we talked about this last class, and if you use your Desmos, if you go to the pre-programmed charts, so let me close off some of these here so you're not confused with what I have open. When you go to the pre-programmed list, and anytime you're working with the table, you need to go to regression models. That's what we were trying to figure out, a polynomial model or a function. And so when I click that one, I have this table that pops up. And so I'm going to just type in our values, which in this one is easy. It tells us the x's are 1, 2, 3, 4, 5, 6, 7, and 8, data up to 2008. And then here's our population. Let me slide this over so we can see the population better. 50, 50, 50, whoops, 55, 10, 56, 08, 4, 9, 6, 5, 2, 0, 1, 5, 0, 8, 9, 5, 0, 9, 5, and 4, 6, 7, 5. And what's happening is right now it's trying to come up with a quadratic regression. But to figure out the scatter plot, I'm going to do this zoom fit. And I'm going to kind of look, and I see it looks kind of like a cubic graph here. That's what it looks like to me. And so what I'm going to do here is go to cubic regression, open that folder up by hitting the triangle, and I'm going to click this and see how good of a model does that look. And when you come up with it, the R squared value tells you how accurate it is. The perfect accuracy would be a value of 1. And so if perfect is 1, you can see that's 89% perfect. Now let me go to quadratic real quick. Quadratic, you can see, is only 80%. It wasn't as good. Linear, these keep dropping. That's only 38%. And you could keep going down and trying to find the most accurate. Ooh, oh, never mind. That's 0.11. So that's not it. Cubic looks pretty good. So I'm going to use this cubic equation. And so here's the equation here with the values A, B, C, and D that I'm going to want for my answer. So let me just slide this over just for a moment so I can write down what we're going to say is that this is cubic. And come on now, right. The equation, a cubic would be A in front of the x cubed. So I'll just say approximately, I'm going to round to 2 decimal places throughout here. Let's just do that. So since I'm rounding, I'm going to do a squiggly equal sign. So 10.02 x cubed. The B is minus 176.32. And that would be x squared. And I know that because the B comes in front of the x squared. The C is 807 point, let's say 47 when I round. And that would be to the x to the first power. And finally, D is by itself 4454.79. So that's going to be my equation that I'm going to use moving forward. So let me just slide this back over a little bit. There we go. And now let's continue on. So and that was a cubic regression. Did a cubic model or regression, whichever way you want to think of that. Okay, so part B now. And I'm probably going to need that equation. So I'm going to copy all this so I have it. On part B, it says write a polynomial function to model the data set. Isn't that what I just did? Create a scatter plot, determine the type of, okay, so this is wanting a cubic. And so I'm going to take this away. Cubic regression off the scatter plot. It says round to the nearest thousandth. Well, I did to the nearest hundredth. And state the correlation coefficient. That's the R squared. This right here is the R squared value, which on our table over here, the R squared was 0.8932. That's what that value is. And we said that was a cubic model. And so over here, I could post in this picture, but I will, yeah, let me do that. Take a picture of this real quickly and throw that in on part A so you can see that on later. If you go back to the notes, you can see what I did there. There we go. And now let's see part C. It says use the model to estimate the population of town in the year 2012, which just basically means you want to know what happens if you put in a 12, if you substitute in a 12. So basically, what is the population when 12 is inserted in for every single x? And you could just type all this in. There is a quicker way. I'll show you the quicker way. And that would be if I close off the other, if I just totally X out the other regressions. So you got to get rid of every other regression other than the cubic you're using. If I eliminated all of these, I could just type this in and use the letter A. So now it knows what A is, the calculator, if you clear out the other ones. Now, if you don't clear those out, it won't know what A is because each one of those equations is trying to give an A. And so I would just say A times, whoops, A times 12. 12 cubed, there we go. A times 12 cubed plus B times 12 squared plus C times 12 plus D. So basically, instead of having an X, you could just copy all that in and substitute the X with 12, and that's the value we get. And so here I've copied everything down, and you can see the population would be approximately, I'm gonna round to the nearest person because we don't have 0.19 of a person. The population is approximately 6,069 people. And now part D, determine the approximate year in which the population reaches 10,712. And so maybe the best way of doing this one would now to be to just write f of x equals ax cubed plus bx squared plus cx plus d, because we have all those coefficients. And when you look at this graph, I want you to notice this is the answer that we have. That's why it's highlighting perfectly over that. We want to know when ultimately that's going to equal the y value now of 1072. So I'm just going to do y equals 1072. And I'm going to look at what year it would be when they cross 10,712. Sorry, 10,712. Here we go. So I need to zoom out a little bit. And it looks like it would cross in year 15. So that would be the answer here on this one, the approximately year 15. Let me post that in there now. Which that would represent 2015. And so that would be the answer here for part B. All right, so now your turn, use this table to come up with your solution.